Okay, welcome everyone. Those that are currently here and those that will be catching this recording a little bit later. I know there's a fair few people who can't be here right at this time, and they always watch the recording a little bit delayed. So I think welcome to all those that are here live and those we'll be talking with later. Last week, we didn't have a workshop on Thursday due to the 4th of July holiday, but on Tuesday we kind of wrapped up our discussion, kind of put a bow on some intro to machine learning topics, basics of machine learning modeling. We talked about decision tree algorithms specifically. We are now going to enter kind of a new phase, a new set of topics here during our workshop. And last time, you guys had mentioned to me that you wanted to learn more about statistics and linear algebra. And so we're gonna talk and kind of introduce from a 10,000 foot view the concept of math in data science generally today. And I want you to get an idea for the degree to which math permeates all of data science, but that you don't have to know all the math that's ever been created in order to be an effective data scientist. And in fact, the level of math preparation you need depends heavily on your goals, on where you want to get to, on the specific job roles you want to shoot for, the kind of professional or practitioner that you want to be, right? And so today we're not going to write as much code as you maybe had hoped. I think it's really important today that we kind of level set and make sure we're all on the same page exactly about what it means to learn math for data science and what math is involved in data science. And really, as I was looking at, you guys had requested specifically, wanting to learn more about statistics and linear algebra specifically, which I think is spot on. Those are two areas of math that are most relevant to data science. But as I was looking at like projects we could do together, I realized that we could probably get a little bit more specific about what about statistics, what about linear algebra we specifically wanted to learn together. And so we're going to start kind of at a high level today and then drill down specifically, and I hope to get your input again. I have come up with some ideas for specific topics and specific projects we can do in some later machine learning workshops. Some of them are a little more linear algebra heavy. Some of them are a little bit statistics heavy. And I'm going to share with you right now, in case there's individuals that are going to be here at the beginning of the stream, but not at the end, a link to and I need to leave this slideshow, a link to a poll, all right? And this poll is with a service called Slido. Makes it really easy for me to send polls to you. I'll share this link in the chat. And let me make sure I can actually look at it. Okay, it's waiting for votes. Can I view it? It's been a couple of years since I've used Slido and the interface has kind of changed. Waiting for votes. Yes, I want to view it as host or as you guys. I don't know. Let me know if you can see this first one here. Do I need to do something here? Copy your QR code, download. Go into ranking. No, I've already got that. View as participant, desktop. Okay, so this is a set of 5 different major categories of math that we could focus on together. I'll explain more about these different areas and the specific projects I think we could do together. But I would hope that by the time you're done watching, that you will be able to help me rank your interest in these different areas of applied math within data science. I just bring that up right now because this is what I hope to culminate in. I see some of you are already starting to vote a little bit. That's awesome. This poll will be open for 3 days. So for any individuals that aren't here live or going to catch the recording later on, you can still vote in this poll. Just click on it in the chat. And I'll also include the link to this poll in the emails I send out if you're on the email lists or in the any social media posts that I make in case you follow Temzee on any of its many social media accounts. But this is kind of what I hope to drill down to. We're going to start at a high level. To what degree is there math in data science? What specific kinds of math? How does that affect us? Kind of what projects can we do together that would be cool and impactful and fun, dare I say, okay? So I just wanted to get that up right here from the beginning. I'm not really going to look at this poll until maybe the end. So you'll have time to think about it and get your responses in there. I'll let you turn this slideshow back on. And I'm actually going to turn off my little bottom right corner overlay of me today because I have a lot of slides here and my face is going to kind of cover up some important text. So I'm going to go ahead and turn off that webcam overlay for a little bit. Okay. All right. In all that preamble, let me make sure that I didn't miss anything that I wanted to say to you. Okay, so one quick announcement is that, again, we will not be having a machine learning workshop on Thursday of this week. I'm actually not sure if we'll continue to do them always on Tuesday or Thursday, or just sometimes on Tuesday and Thursdays, but I know we'll always do them on Tuesdays. I'm trying to balance preparing these lessons with some of the other work I need to do on Temzee.com and other pieces of instructional content I'm doing. So for this week, we're only going to have a Tuesday machine learning workshop. Yeah, you'll hear from me next week because we're going to do another workshop again 1 week from today on Tuesday about if we shift to a Tuesday only kind of a thing or if we keep it Tuesday, Thursday. But for this week, again, we're only going to have a Tuesday workshop. And like always, you'll hear more about that in emails and social media posts if you happen to not be attending this particular session. Okay, so that was the other announcement that I wanted to get out before we get started. Okay, another half of an announcement. So the recordings of these workshops, you may have noticed that they are on the Temzee YouTube channel, and they will always be there. Eventually, I will take them off of the Temzee YouTube channel, and I will edit them a little bit, polish them up a little bit, because there's this timer section when we're waiting for people to gather at the beginning of each of the recordings that I'm going to slice off the beginning. And I'm going to add them to the Temzee website. There's going to be a new section on the Temzee.com website just for these machine learning workshops. So we have an archive of all of the past topics we've gone over and links to all of the important resources that we use during these times, and just one clear place where you can browse all of them, find all of them. So keep an eye out for that as well. Okay. Any questions about those announcements before we dive into some of the slides I've prepared? Okay, keep typing if you do have a question. There is a little bit of a delay. So, okay. Part of what I want to do today, I want to kind of introduce with like a little bit of a metaphor. And this metaphor I call, getting a roadmap, right? I want you to imagine or think about like if you've ever been to like a really big shopping mall that you've never been to before, or maybe you're in Disneyland or someplace like that, and you need to get around. You got to get from point A to point B, but you don't know the lay of the land. It's all unfamiliar to you. And so you find a map, maybe like this one that I've shown here. This is a map I found online of a shopping mall, right? And when you look at a map like this and you're trying to find out where you should go, what is the first thing you do when you come up to a map like this? What is the first thing you would do when you come up to a map like this? Let me know in the chat. Okay. The first thing that I do is I look for this red star. Yeah. So Shroot says, find your own location. Haley says, look at the you are here sign in the destination. Yeah, so this red star usually means that's where you're at right now. That's where this map is displayed, right? And you always have to find out, where am I at? That's your starting place. Well, then after that, you have to identify, okay, where is it I want to get to? With the shopping mall, these are the different stores. They have different numbers. They usually have some kind of like an index where you can find the store you want to go to and see what number corresponds to it. Say you wanted to get to store 34, right? You have to say, okay, where do you want to go, right? Where am I at? Where do I start? Where do I want to go? And once I know those two things, you can chart the path from A to Z. You can figure out, where am I? Where do I hope to get to? How do I get from here to there, right? I find it's really annoying, and this happens more often than I would expect, that I come up to a map like this and it doesn't have the "you are here" star on it, and I'm totally lost. And I end up like trying to look for landmarks around me and then find those landmarks on the map, and it's really annoying. And I can usually figure it out, but having a good feeling about where I am currently and knowing that exact location helps things so much. So like this is obviously a metaphor for, it can be a metaphor for a lot of things, but today I want to think about this as like a metaphor for the mathematics we are currently familiar with and comfortable with versus where we hope to get to in our journeys as data professionals, and what our personal goals are, what we hope to accomplish. And I want to help provide you kind of a map like this today, a lay of the land for what math is required or what math is expected of you, what kind of competencies are expected of you throughout a variety of data science professions. And then we're going to kind of drill down into the data scientist job description and job role specifically, and look at what are the most impactful math topics to be proficient in to be a really qualified and really exceptional data scientist, right? So this is kind of what I hope to do with our discussion today, this metaphor of the map. All right. So again, just to restate learning objectives, right? We're going to look at these 5 different job titles specifically and try and understand, first off, what are they all about, but with a specific emphasis on how does the kind of math preparation that is needed differ between these roles? Because I think that is one of the major ways that we can differentiate between these different major job titles within the data professional umbrella, which we'll talk about in a minute. All right, so we're going to look at the level of math preparation that's needed, look at data scientists specifically, and then we're going to look at our soon-to-be journey about applied mathematics study here together in the machine learning workshops of applied math for machine learning specifically. And we're going to try and identify what we think the most useful topics are, and that's going to kind of lead to some of the projects that I've included in the poll, right? So that's where we're headed throughout the slideshow. Okay, and as I mentioned, there's this big old industry of being a person who uses and can make sense of and make value from data. I'm calling this the data professionals umbrella, right? And there's lots of things underneath this. There's these 5 major job titles: data analyst, data engineer, data scientist, machine learning engineer, and research scientist. Those are the 5 big ones we're going to kind of briefly talk about today. But there's like a bajillion other ones as well, right? Data architect, statistician, business analyst, data visualization specialist, deep learning engineer, ETL developer, data warehouse engineer, business intelligence analyst / developer. I can't even remember all the ones I've already read. Database administrator, AI engineer, quantitative analysis or quant. And then you have more like executive or management level roles: chief data officer, director of whatever, director of pick something else, director of data science, director of data engineering, director of business analysis, director of I don't know of anything, right? Chief technology officers, big data engineers. It's this big old hodgepodge mess of job titles, and they all have overlap. Some have a lot of overlap, some have a little bit of overlap. And the really tricky thing about navigating this industry is that some of these job titles mean different things from company to company to company. I remember a few years ago when I guess it was a lot of years ago now, when I was interested in getting into data science. And I looked up a day in the life of a data scientist video on YouTube. And it was a guy who worked at Facebook before it was called Meta, right? So it was still Facebook. And he talked about what he did on a day-to-day at Facebook. And he's like, I have the title of data scientist. And then he went about his day and he shared a lot of job duties and job tasks that sounded a lot more like what I understood a data analyst role to be, okay? but his job title was data scientist. And then I went to the comment section of the video, and everyone's like, "You're not a data scientist, you're a data analyst. Well, you're not even doing you didn't do any machine learning today, right?" And we're all annoyed with him, right? But like, that's really not his fault. It's the companies that choose the job titles and choose how to use job titles to organize their people and maybe reward people for certain efforts, right? Some of these job titles are coveted, and so they can kind of use those as carrots to accomplish various things, right? But like, what I'm saying is there's a lot of overlap and there's a lot of confusion in the industry about what exactly these roles are. And I hope to provide some amount of clarity to this today. Okay? I know I can't provide perfect clarity to this because there isn't any way to give perfect clarity to this because the industry still is trying to figure it out. But I hope to help you with this today. And then from getting some clarity about the differences between these job titles, help that drive a discussion about math specifically, as I've mentioned. Okay, so this is kind of where we're starting from, the 10,000-foot view. Actually, before we go to the next section, I want to do something with you, and I want to show you that you have the capabilities to get some clarity on some of these things on your own, even if you tune out about some of the next things I'm about to share with you. If you even go to any kind of job search website, and actually I would encourage you to even do this with me. Go to Indeed.com. You're going to see my location here, but that's okay. And search data scientist. Change this to something broad. United States. If you're not in the United States, you can change it to your country. Hit search, okay? And then try and open like 5 to 10 normal looking job ads here, job posts. This is like a marketing specific data scientist, maybe a little specific senior data scientist. You'll see there's a lot of variance to the job titles here. Like, what is an associate data scientist versus a junior data scientist versus senior versus an ads data scientist versus a data scientist in bioinformatics versus a sports analytics data scientist. And like, there's like tons of variations, but I want you to kind of find ones that seem like core data scientist roles, open them up and find ones, skip all of these giant walls of text and scroll down to these bullet points, okay? And try and get an idea about, is there any consistency to the bullet points that are down here? Okay, qualifications, bachelor's degree, some LaTeX, Python, data in R, some related experience, and be a motivated, smart, good communicator person. That makes sense. It's a junior role, so not a ton of asks, right? Another one here. Skip down to the bullet points. Proficiency in R, Python, or other statistical packages. Data mining techniques, that's funny. Tableau, okay, right? And you can kind of go through here and if you read enough of these, you'll start to get an idea about where this job title starts and ends. And you might find that like this umbrella is wider than you thought it was for a particular job title, and that it's not as clear cut as maybe you'd previously imagined. And you'll learn that some job ads do not do a good job at really helping you understand what your qualifications need to be. Like bachelor's of some kind of mathy thing, some statistics, mathematics, like it's pretty vague, right? Here's a senior one. I find the ones that ask for senior roles are usually more specific. This one looks like it's not the case. But we're going to talk about a few of these things here today. I encourage you, if one of the roles we're talking about today is particularly interesting to you, you probably already have an idea about what roles in the field are interesting to you. I know that not everyone who's watching right now is an absolute beginner. I know that some of you are already employed as data professionals, and that's awesome. But I just would encourage you to go through this exercise. And even in fact, I have a data set of scraped data scientist job listings. In the future, we could do some like natural language processing analysis on this and see if we can, with Python and in an automated fashion, try and summarize like what are the topics that are most often, or what are the requirements that are most often asked for in data scientist job listings, or we can really pick any job title that we want. we would just have to scrape a different data set of job listings if we wanted to change the job title. That could be a cool thing that we do. But you would be surprised how good of a barometer you can get, how well calibrated you can get with just reading through 10 or 20 job listings. So that's something I would encourage you to do. Through doing this is part of how I have created some of the next slides in our slideshow here. Right? About like, what is a data analyst? A professional who collects, processes, and performs statistical analyses on large data sets. Their primary goal is to extract meaningful insights and trends from data to help organizations make informed business decisions. Kind of vague. In my own words, a data analyst does some data collection and cleaning, and then uses basic statistics to try and find anything interesting in that data. We call that getting data insights or finding patterns or signal, right? You're using, but it's, in my opinion, whoops, I mean to look here, right? Data analysts use mostly statistics to do what they do. Okay? And I want you to notice that on all of these kind of responsibility sections, I have 3 slides for each job title, right? So we have this overview here, specific skills that might be required, and then like an education section, because in this education section, it'll speak a little bit more to mathematics education and mathematics preparation, which we're going to talk about. Okay. I want you to notice that a big part of the job of a data analyst is not just working with the data, cleaning the data, making sense of the data. It is also communicating about the data, right? Building reports, visualizations, dashboards, presenting findings to stakeholders, working with other departments. There's this big communication aspect to a data analyst's role that I think is really underemphasized in the majority of data analyst educational institutions. You know, they want to teach you how to use Tableau, how to use SQL, Excel, Python, Power BI. Like, they're really focused on specific tools, when I think if you were to talk to any professional data analyst, they would tell you that communication skills are probably the most important set of skills for success in their job, right? You still have to know, at least at a basic level, the statistical tools. And you'll find that a lot of companies may use a different set of statistical tools than you have learned about initially, right? And a lot of companies will say, oh, I can train you up on that. I can train you up on the statistics stuff. And you can get familiar with whatever software we happen to be using in our technology stack. But it's a lot harder to teach you communication skills and problem solving and stick-to-itiveness and all those kinds of soft skills. Like the technical work, the code work, is table stakes. You have to have that to even be in the running for a specific job. And then once you get your foot in the door, what really is going to set you apart, well, in the interview and after, in my opinion, is written and verbal communication, problem solving, and interpersonal skills. And I think that's really underemphasized in general in the industry to learners. And so I'm trying to emphasize it now because I think that is extremely important and not talked about enough. And we'll continue to talk about that through some of these other slides. But as far as the educational component goes, education, some kind of math related bachelor's degree is usually a good thing. And it says here, some positions may require or prefer a master's degree or specific certifications in data analytics. To be honest with you, every single one of these is going to say it may prefer some specific certifications in this field. I don't know of any like tried and true industry respected certifications. There are a couple that like might carry a little bit of weight, but I find that degrees carry a lot of weight, certifications not so much. There's some that are like a nice little feather to have in your cap, but they're not gonna blow anyone away. So take that for what it's worth. But maybe a master's degree, definitely some bachelor's level understanding of a quantitative field, right? You can't be afraid of math, and you have to have some statistics preparation, in my opinion. Okay, so that's data analyst. Data engineer. Data engineer is a really interesting job title because it hasn't existed for very long. Um, Google has a tool where you can see the prevalence of specific words or phrases in the English language. The problem with this tool is that it only has data up to the year 2019. And up to the year 2019, the term data engineer still hasn't really showed up very much yet, right? So like we're talking, this is a job title that has not existed for super long. And of all of the job titles we're going to talk about today, I find that data engineer is differs the most from company to company, right? At some companies, a data engineer is responsible for cleaning the data for a data scientist, making a data scientist's job easier. At some places, a data engineer is more about building data pipelines and making sure the data infrastructure is all wired up and working properly, right? I think that's probably the more common overarching theme about this, right? Data architecture, data pipelines, data integration, as it says here, data security and compliance. It's all the nasty data stuff that comes with having lots of data and having large databases with crazy numbers of tables and lots of reports that need to be run for different departments and lots of different sources of data that all need to come together in some centralized place and making all that work together. And there's actually a lot to that. Some of it's kind of basic, from writing SQL queries and wiring things together and making sure the trains run on time in terms of reports running and things like that. But there's more data architecture level things that are trickier, like where it says selecting appropriate databases, data lakes, and data warehouses based on the organization's needs. In my experience, that's more of a manager level role, right? Your chief data officer or your data engineering manager is usually making those technology decisions, and everyone below them has to live with those decisions. Maybe gets a say, but is not the ultimate decider, right? So also a really interesting role. I'll let you read through some of the technical skills here. You'll notice that all of these mention Python, all of these mention SQL, right? There's some larger like data engineering and big data tools mentioned here, Hadoop, Spark, cloud platforms, data warehouse stuff. So a little bit different cup of tea, still data heavy, still Python heavy, really SQL heavy more than anything, data engineering, right? So education and background, right? Same thing. Needs to have some experience with a quantitative field, maybe a bachelor's degree, and if a company's really picky, maybe a master's degree. In my opinion, the data engineering day-to-day is slightly less math intensive than a data analyst, but it really depends. There's a big giant, it depends, flashing lights thing there. Some data engineering roles can be highly technical, and others are, particularly junior roles, are more about writing SQL queries, making sure pipelines are running correctly, and setting up all the plumbing for the data, so to speak. A data plumber is probably not a bad way to describe it. But the first of these, kind of bachelor's level, math comfort level, maybe a master's degree if a company's really picky, or if you're an overachiever, in my opinion, at least for entry-level roles, I would say. Okay. A lot of what I'm going to say here is with the entry-level role flavor, since I'm usually teaching learners who are trying to break into the industry, or trying to pivot in their roles, things like that. So everything I say is with a slight emphasis that I'm speaking slightly more to junior roles than other roles. Okay. Data scientist. This is the big kahuna, but a lot of stuff gets put under the umbrella of data scientist, in my opinion, shouldn't really be there, because a lot of people want to have this job title. Like that Facebook data analyst who had the job title of data scientist. Maybe he does do more machine learning. He just didn't happen to on that one day that he made the video, but anyway. In my opinion, a data scientist needs to be able to do all the things of a data analyst. And plus, on top of that, statistical modeling, machine learning modeling. So you still need to be able to clean data. You still need to be able to make visualizations. You still need to be able to communicate about You still need to be able to communicate about the data. But now you have added on top of that this component of understanding machine learning algorithms, the machine learning modeling process, and knowing how to make systems that can generate quality predictions, right? We talked about how these models need to generalize well to unseen data. That is now part of the data scientist job description, whereas less so the data analyst's role. It's not that data analysts will never do any machine learning. It's just that on average, that's a differentiator between these two job roles. Okay, so you're going to see Python. Whoops, I want to highlight the text here, but it changes the slide. Python, data manipulation, pandas, NumPy, scikit-learn. We've done a little bit of that. You may need to use more of a data analysis tool, Tableau, Power BI, or Matplotlib, the Python graphing library, which we've talked about a little bit. In your machine learning, you might use scikit-learn, or you might use TensorFlow or PyTorch if you're doing neural networks and things like that. But yet again, a big important part of your job, communication skills, problem solving, being able to work with others. You got to talk to stakeholders and get buy-in for the models you're trying to make and the systems you think are going to be the most useful to the company. And that, yet again, is a really underemphasized aspect of these jobs that I want to try and emphasize, even as we get ready to learn some math, right? With the data scientist role, it will become more common that a master's degree or even a PhD may be asked for in a job listing. Okay, so for some of these roles, you will be filtered out without an advanced degree, or if you don't have significant job experience that may be seen as commensurate or qualifying you to be equivalent to a master's degree or a PhD, right? However, and we're going to talk about this a little bit later, in my experience, many job listings ask for a master's degree out of habit, but usually aren't hard filtering on it. That changes from company to company. Usually governments and universities have more of a hard filter there, but kind of regular corporations will look at your resume as a whole and maybe take your most advanced degree you've achieved as a factor that in, but it won't be the end all be all. Alrighty. So a little bit higher educational expectations here, specifically a little bit higher mathematics preparation expectations here, and we're going to talk about that as we go on. Thomas Day, welcome. Glad you could be here. You and I have already talked about some of these things in the past, and you'll get to see some of that in the future. All right. So two more job roles I want to talk to you about. I'll try and go fast because these have some similarities to each other. First is a machine learning engineer. A machine learning engineer is everything that a data scientist did, plus some extra software engineering competencies, right? Some familiarity with fundamental computer science topics, data structures and algorithms, really making sure that your code is efficient, that it runs successfully, a even greater emphasis on you got to be a really expert machine learning modeling professional, right? But everything you do now needs to scale. It needs to work at to a really smooth, large degree with lots of users, right? All those kinds of things. So we had data analyst, data scientist built on that, adding the machine learning portion. Machine learning engineer has even greater expectations placed upon it. And in my opinion, you'll see that machine learning engineer is a little bit more senior of a job role, typically, pays a little bit higher, typically, and is trickier to qualify for. You have to be a really solid coder in addition to having really solid data science know-how and math know-how, okay? And I'm sounding like, I'm repeating this so much. This whole, skills screen, the second screen of each of these is starting to look pretty similar at this point, right? Communication skills, math knowledge, data engineering, technical skills, algorithm and model knowledge, right? And yet again, the communication skills, so important, Okay, but that's machine learning engineer. The thing I really wanted to get to about this is that many machine learning engineers have advanced degrees, master's degrees and PhDs. You're expected to have quite a high level of mathematical preparation. This is a very rigorous role. You have to be a really cracked coder and math doer, and that is often pretty high expectations placed on individuals who attain this job role. Okay, last but not least, research scientist. And I might not have this job title quite right, but in my opinion, a research scientist is the most academic and has the highest level of mathematical competency expectations tied to it, right? Many research scientists have PhDs. Typically, research scientists in data science hold PhDs in fields like computer science, statistics, mathematics, or a related discipline. They often have a strong academic background with publications in peer-reviewed journals and experience in conducting independent research. Okay, so this is kind of a little bit of a different ball of wax. You're not just a machine learning practitioner. You're just not just training good models. You may be trying to advance the role by developing totally new methods. You're trying to invent new algorithms that no one's ever used before, right? You're trying to be the person that invents OpenAI's next crazy large language model, or creates the next generation of generative AI neural networks, right? Like, you're trying to do things that have never been done before, whereas your typical data scientist practitioner is taking already invented technologies and applying them to kind of whatever low-hanging fruit they can find within their organizations. A research scientist is trying to add new leaves to the tree of our collective knowledge, right? So this is much more of an academic role. This is a very math-heavy role, okay? And the reason why I included research scientist here as a role is because, in my experience, a lot of people conflate the job of research scientists with data scientists, with your average data scientist. And that's because many of the biggest, most famous names in the data science field are these famous researchers, people who are looked up to, people who have kind of paved the way and invented new technologies, people like Hinton and Jan LeCun, and I'm probably mispronouncing all these names, and Francois Chalet, who made Keras, and like Andre Carpathy, who's been at Tesla, and I mean, just like giants in the industry and in the space, and they're technically have a very strong math background, very strong coding background, but are much more academically oriented. And in my opinion, the data science industry has a problem with there being some math qualification gatekeeping and academic level gatekeeping, where people without a master's degree or PhD are sometimes looked down upon, when it's really not that they are doing work that's any less valuable. It's just different work. They're not doing work with the intention of publishing in an academic journal. They're doing work with the intention of furthering business goals and creating business value and justifying their salaries through the value they create, right? And it's not like a less than thing, but I think sometimes if you're not speaking at academic conferences and inventing new things, that sometimes you're I don't know. People can be a little self-conscious about that, and this is one of the things this is why I've gone through this with such detail here. I don't expect you to read everything that's on these slides. If you want to, I'll share the slides with you when we're done today. But really, I want to help you understand that when you go to Indeed.com and you're looking for data scientist roles, you're going to see some roles that are for data scientists that really should be called data scientist researcher roles, particularly the crazy high-paying ones. Machine learning data engineer specialist. Oh, wow, got all three in there, right? But you got to at minimum have a bachelor's degree. They hope you have a master's or a PhD, right? The things I really want to emphasize to you is that, oh, wrong screen here. A few different things, and I'll get down to these in this reminder section, right? So a few reminders going through this. Like, first off, what are the skills that are most important to have on your resume? Well, the ones that they ask for in the job listing. Python, whatever Python packages they want you to have experience with. SQL experience. If it's a data engineering role, you need to have experience with the data architecture tools. You have to have experience with, at least things in that tech stack. You might apply to a company that doesn't use exactly the same tools as your last company or the exact same tools that you happen to have experience with. Usually they'll work with you to some degree, but you need to have the proof of the technical know-how on your resume. And sometimes having a degree in a quantitative field can help with that. I want to say that master's degrees can be really valuable, but they're not the end-all be-all. So a lot of my students in the past would get really dismayed as they go and look for job listings, like, man, everyone's asking for a master's degree. I only have a bachelor's degree. And then they would apply to the ones that ask for a master's degree and still get the job, right? And I can't tell you how many times that would happen. I'm not saying that will always happen. There are some companies that will definitely screen you out based on that qualification. But yeah, we'll talk about that a little bit more. What skills are the most important to demonstrate in job interviews? Well, in a job interview, you got to still have the technical skills, but at that point they become table stakes. Every good candidate is going to have those same skills. So proficiency with the coding and the math just gets you in the running. But what really sets you apart are those communication skills, those soft skills, and you communicating that you're on a trajectory of growth, that you're hungry to learn and hungry to improve and hungry to contribute to the company. And that's really what can tip the scales in your favor in job interviews. And it's a little bit different than what's on the job description. It's a little bit different than what's necessarily on your resume. It's good to communicate these kinds of sentiments in your resume and your cover letter as well. But these soft skill competencies are extra important to demonstrate in the job interview. Like, what will you spend the most time on the day-to-day? What will you spend the most time on during your day-to-day? Well, probably like data cleaning. Probably something that's like barely on your resume, barely on the job description, barely talked about it in the job interview, right? So I find that there's quite a lack of congruency between like what is filtered for in the job application process versus like what the day-to-day looks like. And you have to make that transition, and you have to, check the right boxes in the application process. And then it's a little bit different flavor of work and what helps you excel once you're on the job, right? What's the most critical skill for success once you have the job? Communication, interpersonal skills, working with stakeholders, getting buy-in, all those kinds of things. You still have to do the work. You still have to fit the models. You still have to clean the data, right? But like, you can Google stuff. In a job interview, you might be a little uncomfortable Googling, what was the equation for such math thing that you studied 10 years ago and you've forgotten, right? You're going to be more panicked about that in a job interview. On your day-to-day, just look it up. Who cares, right? So it's this funny game we have to play in preparing technically, preparing with our code skill, preparing with our math skill, proving that we have those skills through a resume, through job interviews. Maybe having a degree can help build some of that authority. But then transitioning to the job, the game changes a little bit. Those things are still important, but other aspects become extra important, right? So I just want to emphasize, in a perfect world, the answers to these 4 questions would be the same thing, right? But they're not, right? The more eyes open we are about that, the better prepared will be, the more success we can have, right? So here's another reminder. What percentage of data scientists have an advanced degree? A master's degree or a PhD? Okay. Well, according to this data set, I found a lot of different data about this. And I picked the data points that I chose to include in here seem to be like middle of the road stats from what I saw. They weren't extreme in either direction. So I've tried to be selective in these specific statistics that I'm sharing with you. You feel free to fact check me and do your own research, particularly about this slide and the very next one. Okay, but this also kind of matches my own intuition and my own experiences in the industry is that, maybe somewhere around, what's this, 47% of practitioners, people who are already in the field, already have the job title, have an advanced degree. But the majority just have a bachelor's degree, or not even that. But typically at least a bachelor's degree, because you do need to learn some amount of math and some amount of programming somewhere before you get into the industry. However, I don't know why I don't have this full screen, but oh well. Right? What percentage of job listings ask for or quote unquote require an advanced degree? Well, somewhere between like 60 to 80% of data scientist job listings ask for a master's degree or a PhD. Right? So a much higher percentage of job listings ask for these advanced degrees than people in industry actually have. And part of the reason for this, in my opinion, is that because there's different expectations of direct hires, outside hires, than internal hires within companies, right? If you're going to hire someone who you've never met before, you're going to sandbag a little bit and maybe filter a little bit harder based on them having a master's degree or PhD. But if it's someone you've worked with for a year in a data analyst role, and they've slowly taken on more data scientist-like job duties, and you're like, wow, that person's really crushing it. Let's move them onto a new team, give them this new title of data scientist, maybe they get a raise, I don't know, reward them for their hard work. Like that internal hire, it's easier to make that shift internally without having the advanced degree than it is to come in as, a resume that lands on somebody's desk and to not have the advanced degree, right? So it's easier to pivot, it's easier to move within a company without the degree filter than it is to move between companies with the degree filter. So I think that's part of the explanation for this discrepancy here. A greater percentage of job listings ask for advanced degrees than really people in the industry actually have. So what I'm really trying to emphasize with this is don't let a job description, particularly for a junior role that asks for an advanced degree or a master's degree, don't let that scare you off. Apply anyway. Try for that job anyway. And probably better than any of those things is network and meet people and show them how awesome you are, and let that be what gets you the job rather than you saying you have a certain credential. Anyway, that's my little soapbox. Okay. Job listings are closer to wish lists than they are checklists. This was a study that was done that I think had like 1,800 different candidates and checked how good their qualifications matched up to the requirements on the job description. And you'll notice that the higher the match, the better fit they were for the role, the higher their likelihood of getting an interview. But once they became like about 50% qualified, they met about half the requirements of the job description, their likelihood of getting an interview didn't really go up after that. If you matched like 90% of the requirements on a job listing, you might be seen as overqualified. They might go, we don't want to invite that person in. They're going to ask for too much money or something like that, right? And so you want to be qualified, but not like super mega qualified. You don't want to be underqualified either, right? You want to be in this sweet spot. Companies usually want to hire someone that they know they're going to be making an investment in. They're going to want to train you up a little bit. They expect you to get better and you to learn on the job over time, right? And so this graph is always fascinating me. The other thing I think is fascinating about this is that like no matter how qualified you are, your odds of getting an interview stink. They're all less than 10%, which 10% is actually pretty high. Like if you're blindly applying to jobs on Indeed, expect like a 2% rate. It really depends on the quality of the job board, and your odds go way up again if you know somebody, if you network your way in, if they already know who you are and know what you're all about. Your odds go way up. But job listings are closer to wish lists than they are checklists. So don't be intimidated by job listings. Do your best, be your best, show that you're awesome, and it'll work out for you. All right. And another thing I just want to say is pretty much everyone is self-conscious about their math skills. Even people who've been in industry for 15 years, they haven't studied probability theory or calculated the derivative of a linear algebra matrix by hand. They haven't done that for a decade and a half. They might still ask you to do it in a job interview because they don't know what they're doing. But like the knowledge you don't use decays over time, right? And so the math you're going to remember, the math you're going to be the best at, is the math that you are applying on the day-to-day to do stuff, right? And I want that to play into some of our discussions about studying applied math for data science, okay? And some of the topics we choose to study together. Right? Okay, so this is how I would kind of vaguely describe the amount of math preparation that's needed for any of these given roles. Data analyst, it's mostly statistics. Statistics 101, probability theory, be able to make some, do some data visualizations, communicate about data. Yeah, some basic stuff. Data engineers, same thing, statistics 101. You might add in like some set theory and graph theory, but in my opinion, or some CS fundamentals algorithms, those things might be asked in job interviews. In my opinion, they don't come up quite as often on the day-to-day of the job. You may disagree with me. It really depends on the job, really depends on what you're doing specifically on the day-to-day. But a little bit of math preparation is good there. I think it's more important to be familiar with data warehousing tools and be really good at SQL queries and things like that in those roles than it is to be totally tip-top sharp on your college level math. Data scientists, again, statistics, add in a lot more linear algebra here, as a lot of the machine learning models we use are linear algebra heavy, particularly models that are used for natural language processing, analyzing text data. After we take all those words that are in the text, we try to make sense of them, we pull them in a big grid, we hold them in a big matrix, more or less. And so there's a lot of linear algebra involved in natural language processing. There's a lot of linear algebra involved in neural networks in general. Neural networks are basically linear algebra machines. You put some data in, the computation that happens in the middle is linear algebra, and it spits out prediction numbers on the other end. And that's a neural network. That's a very, very crappy explanation of a neural network, but that's a neural network, right? And there's a little bit of calculus here as well, particularly in things like gradient descent and doing optimization, what we call optimization with calculus, where we're trying to find the minimum or the maximum of some kind of a function, because if we get to the minimum of a loss function, like that's where our model's going to work the best. That's where our model's going to make the best prediction. So there's some calculus, maybe even what we call differential calculus, not integral calculus as much. There's going to be derivatives and a little bit of partial derivatives as well, some multivariable calculus as well, but not as much as you would maybe think. It'd be good to have some calculus know-how, but by and large, it's statistics, linear algebra, some calculus sprinkled in. Some academic guy would get pissed at me for saying that and may strongly disagree, but as a data scientist practitioner, that's been my experience, is calculus does not pop up as much as the pure math lovers would make you think. Okay, machine learning engineers, like we said, it's all that and more. Probability, statistics, linear algebra, calculus, computer science fundamentals, and really you have to know backwards and forwards all of your machine learning specifics to make the most of machine learning systems. Research engineers, all the math. Like, I don't even know. You might have to invent new math that's never been known by the world before, right? Like, I guess it's pretty crazy. That's why you need a PhD, because you need 8 to 12 years of learning how to do the math. Which is scary, but that's why they pay well. So you see there's like increasing degrees of math preparation that's needed here. Okay, I've kind of probably emphasized that way more than enough. So where do we want to start, right? What to you would be the most interesting places to delve into here? And I think this is actually an extra slide. I didn't mean to have this in here. As we look at studying math together, math for machine learning, math for data science, I want to help you understand that I view this as there being two distinct approaches to learning math. Both are pretty good, but I want to suggest we take kind of a hybrid approach. here's the two different approaches, and they're two different ends of a spectrum, right? We have the from first principles approach, where we learn everything. We work up from ground level. We learn our ABCs step by step, and it's a long road until we get to like something advanced and cool and fun. But we're going to understand the fundamentals super well, right? If we take a from first principles approach, we eat our peas and carrots, and we really make sure that there's not gaps in our knowledge. We have strong math intuitions. If you were to go to a university, they would force you to have a from first principles approach. You can't take that course until you've taken this prerequisite course, and the prerequisite course is pretty thorough and has you do a lot of hand calculation and work with paper and pencil. Right, that's kind of a from first principles approach. The opposite end of the spectrum is only an applications-based approach. You don't ask, what's the math I need to know? You ask, what's the cool thing I want to make? And then you work backwards to figure out, okay, what math is relevant to that cool thing I want to make? And then you learn only the math that's relevant. And the goal is making cool stuff with as little forced math learning as possible. Okay? And I think somewhere in the middle is probably the right approach, right? Sometimes it's good to take a break and say, okay, first principles, like let's take a day and let's just like make sure we really understand variance, standard deviation, correlation, like some basic things, because they're important. And then other days it'll be like, let's just try and make the awesomest thing we can, because that's what's fun and that's what keeps us engaged and that's what keeps us coming back for more, right? And so this hybrid approach is something I hope to take with you. Is we're not going to start from square one and plow forward with like really boring work, but we're going to the problem with the applications only approach is that it can leave a lot of gaps in our knowledge. There may be some blind spots to our math preparation, and when those blind spots may get exposed, particularly in math heavy STEM hazing ritual type job interviews, where they ask you to like do an integral by hand, and you haven't done an integral by hand in 10 years, and you say, I would type it into Wolfram Alpha, which is what I've had to say in job interviews before, and it has not always gone over well. But that's the reality, is like, I've forgotten mostly how to do integrals by hand. I know. But backing up, right? The applications approach can leave some gaps in our knowledge. The first principles approach doesn't leave gaps in our knowledge. Only applications is really fun. First principles is less fun. It's more of a grind. I hope to blend this in a way that keeps us engaged, yet minimizes the amount of gaps that we have in our knowledge, right? Because really, in reality, it is a long road from first principles to the advanced stuff. This is a tweet I saw last month. A person says, it's funny to see people learning machine learning from scratch via fast.ai, which is a pretty good machine learning website, right? It's such a long learning curve to transformers, which is that's the shiny object right now, right? OpenAI and ChatGPT and these large language models use a particular kind of neural network called the transformer, right? So if you start from square one with linear regression, logistic regression, gradient descent, neural networks, multi-layer perceptrons, recurrent neural networks, long short-term memory networks, recurrent neural networks with attention, causal self-attention, decoder-decoder architecture, and then finally GPT, right? That is a lot of steps along the way from going from the first principles approach. And this person says, and I didn't even mention embeddings, models, encoder-decoder models like BERT, Roberta, DeBerta before GPT. I personally would have found it very intimidating to learn all of that from scratch to GPT. And I, as an instructor, I agree. It's intimidating and it's a lot. It's honestly a lot. It's going to be a lot of machine learning workshop, 1 hour weekly sessions if we go whole hog from first principles. It says, I think people usually skip around a lot and try to watch Carpathy directly, Andre Carpathy, who's a bigwig in this space. On the flip side, people who are going top down, which is the only applications approach, right? On the flip side, people who are going top down without knowledge of prior deep learning, like they watch the 3 Blue 1 Brown, which is an amazing set of videos about neural networks and linear algebra and stuff. They learn about neural networks and they go straight to transformers, LMAO, right? You think that's a crazy thing to do. Having fresh eyes might allow them to approach at least applied large language models, LLMs, and hacking on those in innovative ways. Maybe you won't be as dogmatic about your approach to some of the advanced models because you're not as biased by the way it's always been done, right? Maybe you'll be able to think a little more freshly. But in my experience, you eventually need to have a from first principles level understanding, but you can get that jumping around a little bit, right? We're going to try and have this hybrid approach. So if I myself had to start over from today, learning math for data science, here's what I would do. I would learn basic statistics first. And I mean like really basic statistics, descriptive statistics. And I mean things like mean, median, mode, variance, standard deviation. Learn about types of data. We've already talked about that a little bit with continuous variables and discrete variables, categorical variables. I would learn how to make basic data visualizations, learn about the normal distribution, basic sampling, difference between population and sample, very basic hypothesis tests with t-tests, chi-squared tests, maybe even ANOVA, right? I'd learn about confidence intervals and I would culminate in linear regression. What does this sound like? This sounds like any college statistics 101 course. And you can go to Khan Academy and you can get this if you want. You can, if my hybrid approach is too jumpy aroundy for you, there are tons of places on the internet where you can get Statistics 101 help that will cover all of these topics and then some. Okay. I think you also need a little bit of probability theory. This list is probably longer than it should be. You need to understand randomness and how it affects things, random variables, probability distributions, conditional probability, Bayes' rule, and particularly covariance and correlation. We could talk about covariance and correlation here in the basic statistics section as well, but there's some important topics here. I would say that these probability theory topics don't pop up quite as often as your basic statistics stuff does, but still important. And then really the big kahuna, in my opinion, is linear algebra. Linear algebra is so core to so much of the most advanced machine learning nowadays. Because the most advanced machine learning nowadays is neural networks. And as I mentioned, neural networks are basically linear algebra machines. And so topics like learning about vectors, dimensionality, matrices, basic matrix operations, linear transformations, vector spaces. There's a lot of fancy terminology here, right? Linear dependence, eigenvalues and eigenvectors, maybe the fanciest terminology of them all. Orthogonality, which just means things being at right angles to one another. Something called the least squares solution, which is the same thing as linear regression, but done with matrices. Principal component analysis, singular value decomposition. We'll talk about some of those things, right? Like linear algebra, I think gets you the most bang for your buck in the fanciest, most powerful machine learning models nowadays. And basic statistics is the most table stakes, most absolutely basic stuff you have to have, okay? So here's my recommendation. And these are 5 sets of categories that can all lead to lots of really cool projects, but they have different areas of emphases. And this is what I want you to rank your preferences about in the applied math projects that we do together in the future, right? Probably the most basic section here, exploratory data analysis. That is going to cover our basic statistics section, right? We're going to be able to talk about all these things in the context of exploratory data analysis. Make visualizations, do univariate analysis where we analyze just one single column of our data set, bivariate analysis where we look at how 2 columns of our data set relate to each other. Maybe one of those columns is our y variable, our target variable, and another one is an x variable, one of our predictors. Want to understand how those relate to each other. How do they correlate? What's their covariance? All the fun things. And maybe do some basic hypothesis tests. Hypothesis tests pop up here and there, but the basic intuition around p-values and normal distributions and the central limit theorem, I feel is just like really, really important. But that would be kind of an exploratory data analysis emphasis, which we could have in some of our later workshops. Next is linear regression. With linear regression, we get to talk about some basic statistics stuff, but also some probability theory stuff. Variance and standard deviation, correlation and covariance. If we're doing linear regression for inference, we get to talk about t-tests. We can also do linear regression for predictive modeling, and in that case we would talk more about regularization techniques. There's like 3 or 4 ways we could fit linear regression models. One of those is by using gradient descent. And if we talk about gradient descent, we can throw in a little bit of calculus. We talk about optimization problems with calculus. So this is like still some basic statistics stuff, but a little bit more advanced than exploratory data analysis. Okay. So I'd say if you want to do statistics, and that's like the thing that you most want to emphasize, I think you should rank these two, one of these two, as being your highest priority in the poll that I shared. The next 3 are pretty linear algebra heavy. Principal components analysis, or PCA, is a crazy topic. Usually when we apply principal components analysis to a data set, the end result is not like super mind-blowing. But if we do principal components analysis in conjunction with like some other end goal, it can do some cool things. Like, so wait, what is PCA? PCA is a way of taking a data set that has lots of columns, retaining as much information as possible from that original data set, but squishing that information into less columns. It's a data compression algorithm for our data set. That's an analogy. It's not exactly a data compression algorithm, but like the short of it is that PCA, applying it requires the knowledge of a lot of linear algebra topics. In my opinion, if you can follow the steps that PCA takes to compress its data, you're in a good spot with your linear algebra knowledge. You got to know things about variance and covariance, so there's a little bit of statistics here, but then there's linear projections, linear transformations, eigenvectors and eigenvalues. There's some kind of gnarly stuff that goes on in taking a data set and squishing it into less columns. And so that could be a good intro to applied linear algebra topic. Next is kind of natural language processing. Processing text data at large uses a lot of matrices and vectors, grids of numbers and rows of numbers, right? And there's a lot of cool applications of linear algebra, a lot of low-hanging fruit here, particularly with like cosine similarity and other things like that. So if you're really enamored by large language models and some of the text models that exist nowadays, but you also have a hankering to deepen your linear algebra knowledge, then this natural language processing topic would be your cup of tea, right? So PCA is really a linear algebra heavy thing. NLP is also linear algebra heavy, but text data modeling with an emphasis on modeling and doing predictive stuff with text data. And then the next is neural networks. Neural networks is kind of the big kahuna of machine learning right now. And there's lots of really cool different neural networks. They all by and large do linear algebra, but the gradient descent, which is kind of the heart and soul of how neural networks learn and how they adjust their inner parameters to be able to make good predictions, uses some calculus, some derivatives, and the activation functions that are within neural networks also use derivatives through a process called backpropagation to update the weights and biases of the neural network. So there's a little calculus thrown in here too. There's even a little bit of statistics, but by and large, there's a lot of data processing and linear algebra here. And these are just a whole bunch of different common neural network architectures that we could focus on. CNNs, convolutional neural networks, are used particularly for image processing. So if you want to do some cool image stuff and not only text stuff, we could do some of that cool stuff here. But RNNs, LSTMs, and transformers are also very NLP heavy topics. So we could get some natural language processing in here as well. But this is probably the most advanced set of topics that we could focus on. And I'm curious, do you want to start with more basic statistics? Do you want to go deep into linear algebra? Do you have a hankering for text data? Or do you want to just do the coolest, most advanced stuff possible with neural networks? Please visit the link here, slido.com. Help rank some of those things, and we will use your responses to plan next week's workshop. All right? Okay. I realize that was a lot of me talking and a barrage of information. A lot of things you probably even already knew. Okay? But I really wanted to make sure that we were all on the same page, even if I was rehashing things that you were already aware of, so that we could make sure we were starting together as we enter this new phase of our machine learning workshops together. Are there any final questions before we wrap up for tonight? We're a little bit over the hour mark. Remember that the poll is open for 3 days. I hope to see your responses in there. I'll be encouraging you to respond in an email and in some social media posts if you follow Temzee on the different social media channels. Thank you for being here. Thanks for listening to my blabbing. And we will do more cool stuff. We will write more cool code a week from today. Tuesday, there will be no workshop on Thursday of this week. And we'll see how we feel about doing this twice a week or once a week going forwards. And you'll hear from more from me about that. Okay. So, thank you, everyone. Thank you for being here. And I will post this recording on LinkedIn, Twitter, other places in case you want to catch this recording after the fact. For those of you who are here live and participated, thank you so much. And I will see you at the very latest 1 week from today. Thanks, everyone.